Hello again. We continue with our mini-series. Let me first perhaps recapitulate what we have done so far. We have introduced time as a totally ordered set. Totally ordered was defined as a partial order with some special property. I'm not going to go into detail again, but so this time is for the moment not a vector space, not a vector space, not a real line, just a totally ordered set. And that's all I need in the whole theory, in fact. So then we defined something over the spaces ut. The uts were the moments. At moments we had the space, not the space, the set ut, which is the state t. The partial order or the total order of time is in fact the total order of the states of the universe. By the way, I can include, this makes time travel completely impossible. Time travel is absolutely impossible, because you have to redo. If you go from t to t prime, you cannot go back to t unless you change the whole universe to the state before. So even the greatest supercomputer cannot do that, of course. This is impossible. Time travel is for science fiction. And I will talk about some retro things in quantum physics which are completely explainable by my model, which goes back to moments and not to the past. Okay, good. So that was about time. Then I have these maps connecting the states. There will be some geometric or topological maps if you like. I defined over this some ST, some set of things, and they are germs or potentials, germs of existence. Why? Well, because in some intervals, some object AT will have a manifestation. Over an existence interval, the string of the STs for AT, it starts at AT, and then you have the images for the strings. And then you say that exists at the interval. I stress that again. It doesn't exist inside the interval, not at the end, not in a moment, at the interval as an existence moment. Okay, so then we have a string for a given AT, a set AT of a subset of ST. I have the images under the S's, and when I say AT prime, that means the image of AT for that map TT prime here. So it goes from T to T prime. Okay, it's a shorter notation. So we have strings of subsets of STs. And I have realizations, I call it a realization of the string on existence intervals. Okay, so I have a first AT here, and it exists as over this interval, which I call the first interval of A. A denotes the object. So the existing object, I use the A in the notation to say, okay, this is a set and this maps and so on. But the A will be the name also for the object that is represented by this string of things. So the object is a process. Process for object A. Okay. And in intervals, I have manifestations of the object, and manifestations are existing. The object exists at this interval. And this goes to a point, an existence point, if you want. Existence moment. It's not a real moment. I say that to make it clear that it exists at the interval. So, okay, then I am in a new time here, the end of this thing. Let's say this is T1. There's another existence interval maybe. So here this set AT1 goes on and on and on, and there's a second manifestation. So a consecutive manifestation. Consecutive manifestation, the new existence interval starts with the end, and included that, it's a closed interval. Starts with the end and has another end, T2. Second interval, second manifestation. So I can go on with consecutive existence intervals until some moment something happens. This is at the moment, let's say Tn. There's a finite number of moments I'm considering because, well, I only have a finite life, and maybe I haven't said that T is infinite or not, but it's not so stupid to assume that it's infinite, but existing things can be finite. It can be a finite number of existing. By the way, okay, let me say this. If you use real numbers like in physics for T, and use my definition of existence in intervals, so closed intervals, then it's funny that the real numbers, infinite, closed intervals here, closed connected intervals, are countable. Real numbers, uncountable. We continue. Yeah. The real numbers are very infinite, much more infinite than the rational numbers, let's say. The rational numbers are countable, the integers are countable, the real numbers are not countable, but they are continual. But the closed intervals here, they are countable, because every closed interval in the real contains a rational number. That's an easy property for the completeness. R is the completion of Q in some topology for the order and so on. Mathematically, that's easy, but maybe people don't know that. But any closed interval of real numbers contains a rational. And so there is at most so many closed intervals as rational numbers, so countable. So not finite, but countable. That's good. I mean, countable is much better than continuum for many reasons. It's like the rationals. They are sort of isomorphic. Countable, it's two sets of the same cardinality. You can make a bijection. Whatever. But that's interesting to know, that even in the real numbers, the existence is much less infinite than the real numbers, if you have the right definition of existence. So in a closed interval in time, I will assume, but that is not necessary, but it's sort of practical, that there is a finite number of existing things. But in physics, people accept that there is a finite number of existing things, although that number must be incredibly big. You cannot even think how big it is. They have some estimates, but okay. So what happens? I have an existing thing and it manifests itself in a series of things which are consecutive. There's no other existence in between. And then this set here, this is at ATN. This ATN does not realize to existence. So there is no consecutive manifestation. But it could be that the process never is realized again. That means that's the end of the line for existence. Or it starts again at t n plus 1, let's say, here. And then there's another, all these intervals are different. You can think that for same manifestations of the same object, that the intervals are the same, but they needn't be. And I will explain, maybe today or tomorrow, in the section, that the identity problem for an object in different manifestations is not trivial. If I throw a ball against a wall and I catch it back, is it the same ball? You will say, yes, you identify it, but it's not exactly the same ball. Some things, some atoms have changed, something from the wall, something in the collision, something inside the structure changes. It is not exactly the same ball, but the differences are so neglectable, we think, that you neglect it. But this is the same for people, but some people have different shape of earlobes. Are they humans? It's a mutation. It's not the same. They have some genetic difference. But the genetic difference is so small, and of course they are humans. So humans are making a lot of identifications, like categorization in the sense of Plato, that you make a category of things, and you don't really care too much whether the things in the category are really identical or not. So the identity principle in this theory will be a bit dangerous. You have to be careful. It works, but it's okay with some approximation. Anyway, so here nothing continues, but at a certain moment there is an ATN plus 1, and this realizes. So at a certain moment it begins again, and I call the interval J1 A prime. It's not the same object anymore. So this A prime is a mutation. I call that a mutation. So A changes to A prime. Mutation. And then you have consecutive existences of the mutation. And then until it changes again. So, what is clear, of course the name mutation, I got it from biology. I said my inspiration comes somehow from biology. This is exactly how mutations in biology are going to happen, of course. The changes, and what changes? Something genetic, and the original one does not continue, but something else continues. And how different is it? It can be very different. In fact, from the theoretical description, you cannot explain how different it will be. But if you look in nature, you see sometimes some mutations like Siamese twins and things like that, but they don't continue. When the changes are too big, it's not something that lives on. It will normally go extinct. If the mutation is not too big, it can continue, like earlobes or something. So, okay, we have now the abstract notion of mutation is just this: the existence intervals do not continue consecutively. There is a period that it is nothing happening, and then here again it realizes to something, but another thing, a different thing. But they have the same long sequence. So the object A, when I say A, what do I mean? I mean the existing thing. So when I give names to the potentials, I will say pre-thing, pre-interaction, pre-object, pre-event. I can make everything pre. That means it is at some moment, it's an AT, realizes to thing, interaction, object, animal, it can be a pre-human. So I can act as if I'm a kind of God looking at the process, and I know what the result of the existence will be. And then I give the name with pre in front of it to this abstract set of potentials. So AT is potentially an object or an interaction, potentially a human, potentially a lion. You can do all these things. It's just a name. And of course, when I am at moment T and I'm looking at these very short strings of things going on, I don't know what it will be. But if I know, I give it that name. That's all I say. So this is interesting, describing the relation between the change and the existing things is already given in the name, let's say. This is harmless, it's nothing special in fact. Okay, so I have now these mutations, Another thing I should remark is that, okay, I have an I1 of A, so I'm not going to write the whole system again, but it's clear now. This is the existence interval for A. I have an I2, make it a bit longer, I2 for A. So, existence moment 1, existence moment 2. Yeah. So when I think in existing things and I forget all the rest, these are like moments, but they are intervals in reality. So that is the principle of the interval moment. Strange interactions. Moments in the interval and then interval as existence moments. Okay, so I have this. So here is now a chain of existing things. Pre-things come to things. Things is generic name for whatever it is. Okay, but you see, if I look at this interval now, interval k starting in the middle somewhere of this first interval and ending at the second interval, then it doesn't exist here. So the two existence moments are separated by a lot of non-existence. So that means that existing is discontinuous, which is a rather important observation. That's important. And of course in physics they don't care, it seems. They use the real numbers in continuous existence, accepting what is called the granular structured universe. Some people study that. That is discrete. Discrete. Topologically discrete. And it gets worse with observed. So that will be the next step. But, so for example, well, let me first continue with observations now. There's a lot of things I have to say, but I will make a jump to the next lecture and mix it a bit up. So let me first maybe now jump. Observing. Because then I can compare existing and observing. Well, what is observation? Observing is a process, an observation process. And there is an observer, let's say X, and an observed A, another type of letter. Okay, an object A and an observer is also an object. So this is a process, a string process. This is also another string process. So observing means that we have to interact. So there is an interaction. XA. And an interaction is also a process. Also a string process. So I have to have an observer and an observed. They exist sometimes, not continuously, but discontinuously. So you have to exist, the observer has to exist, the observed has to exist before you can observe it. Otherwise you don't know that it is there and that you can observe something. So you have to think that it exists and then begin to observe, right? So the processes are now interacting as processes. So the interaction as processes. Okay, so let me define that abstract notion, and then you can see what it means with observation. I have IXA, where X is an element of X, A is an element of A. This is a pre-interaction. And let's do it at the moment T. Hold on. I have sets xt, sets at, t varies over the time. I have an interaction in st. Interaction is also a germ, a potential. So when I look at the interactions of xa at moments t, so not one thing but the whole set, then that is just the set of all interactions. So xt. So you take interaction between two elements and you take all of these things, that's a big set of interactions between the two sets. And then you have the maps st t prime on I xt at. And where is it? Where? So now I have to go back to the definition of the ST. The ST do not preserve inclusions. You can assume that, but that is much too narrow. Then you get a lot of things which go wrong. They do not preserve inclusions. So that means that if AT is in PT, then it does not follow that AT prime is in PT prime. For example, even if I would look at a set consisting of one AT, and I take the ST T prime of this is not a set AT prime, A prime, T prime. It is a set, the notation is a bit strange, but it's something like this. It's another set. It's the set corresponding to that set, but it's not an element. Set one. So it means that the correspondences, it's very important, the correspondences do not come from maps on the elements. That is the correspondences. Because maps on elements, of course, define the correspondence, but correspondences are more general. Are not coming from maps on ST. You have maps on ST, you have correspondences. The correspondences are maps on the PST, not on the ST. They don't define a map. They don't respect inclusions. So, what is thrown? What is now with these interactions? I view interactions, pre-interactions. I view them as things which are going to realize to existing interactions. That's why I give them the name pre-interaction. So, if it's going to go to an object, not an interaction, then it's pre-object, and that's different. So, but I want this characteristic of being an interaction to be preserved by the STs. So it does not have to be equal to the is not equal to the I of the primes, but it is inside that. So the right assumption is, that's an assumption, it's a demand, an axiom if you like. I have very few axioms, but this is one. no, this is a part of the AT problem. Since I give the name pre-interaction to something that will lead to an existing interaction, if I look at what happens at T prime, it has to be an interaction at T prime also. So I need not equal, so not necessarily, it can be equal sometimes, but not necessarily equal, but inside, contained. Yeah. So that is the characteristic of being an interaction is preserved. You can use this for everything you call pre. If you say just potential, you don't know what it will realize to. But if you say pre-object, pre-interaction or something, then you assume that you know, you're a God, you know what it will become. And then this is a very logical assumption. If it will really go to an existing interaction, then at every moment in between it will be in the interactions of at the moment. But you cannot do that. You can do that with humans. You can do it. You can say a pre-lion. Well, then the pre-lion goes to the inside the pre-lions. It stays there because it will end up with a lion. Okay. So this is a kind of characteristic of the process. Because you know, if you know what it will lead to, you can say that is a characteristic that is all over the process. So the characteristic of the end result should exist on every step. That's an axiom. That's an axiom. I only use it for interactions. I don't use it for lions and other things, but it is the same thing. If I define fields later, like quantum fields, force fields, I will use the type, and this is a type if you want, or type. This is of interaction type, and then all the things are interaction type. If I am not God and I don't know where it goes to, then I cannot say that. So I use this kind of divine knowledge by knowing the whole theory, or acting as if I know the whole theory, by doing this. So I am, of course, I have to describe the universe and the evolution of the universe, so I cannot do another thing than to act as if I know the evolution already, because I want to describe it. But when I realize that's what I'm doing, then it's not harmful, because this is an logical axiom, tells you that the result means the characteristic of the construction. When you construct something with bricks, the characteristic is of bricks. Yeah? If you construct something with electricity, some network or something, the characteristic will be electricity. So that's true for all the things in nature. The things that it evolves into give you the characteristic of the process. It is almost self-evident, but it is not really. It is a sort of axiom, but a very plausible one, I would say. Okay, so now with observation, I have observation is an interaction. An interaction between processes is thus given by interactions between the things in the process at moments. Moment-wise, you have interactions, and they define the interaction with process. Okay, but now I said that the objects have to exist before you can observe them. And the observer has to exist. And they exist in separate intervals and not in the same. So what happens is you have a chain for the object A. So this is A1. R2A. I will draw only 3, the rest goes on. these are the manifestations for the object A. I have manifestations for X, for the observer, and it's longer, for example, or shorter and longer. You don't know. Longer or shorter, everything is possible. I will make this one shorter. The duration, there is no duration of the intervals, there is no duration of time. So it can be longer, it can be shorter. You can also make another action, but as I said, my theory has to be generic. I don't want to impose conditions which are not necessary. But you can say all the existence intervals are the same. The minimal length, like a Planck length for observation, there is also Planck length for existence. You can say if you like, but I don't do it for the moment. Okay, so now this exists here. If I look at this interval for X, it ends in the same moment as the other one, but it begins in another. So now you can say that the A's, the X is here. So let's say an xt double is the same in this interval as in this interval. So the information in the set xt double does not depend on in which interval you view it. So this interval ends at the same moment, but starts at a different moment. But this information here comes from that information in the big interval, but restricted. So it is plausible, but maybe that's a second axiom, which is not essential. You can avoid that, but I have to write more if you do it. Let's say that for easiness sake, we assume that this interval, this I3, is an existence interval for X. So the end moment of the existence interval determines what it goes to. And you can take a shorter interval, but there is a shortest. There is a shortest. So it's given by the beginning element then, and if you start with the end moment, there is a shortest one that leads to that. That's also an axiom. But if you put another axiom, that is, there are a finite number of existing things, then all this follows from the finiteness. If you say there's a finite number of things existing in that interval, which is what most physicists believe or assume, so then you don't have to worry about these things. The shortest is always possible then. Okay. So this leads to some kind of identification of different existence intervals by the endpoint. So, but we said it exists at the interval. So that is the same, if I do it here, that interval goes to the same moment here, yeah, the same existence moment. The existence moment is then a class of existence intervals. Okay. Now, then you can say, okay, they end at the same time now. Then the next observation can be about the existence consecutive manifestation of the thing. So when you observe something, the conclusion of this is observe not the first manifestation. You experience perhaps that something exists, but you don't know what it is. You have to observe it. Then you have to look at it or fix your tools on it. You have to do that, and then you observe one of the next. One of the next. The observance interval contains all these intervals. So the observance observance interval is bigger than several manifestations of the observed. And also of the observer, because maybe you exist several times before you do the observation. Also, now this is rather devastating for the theory. Well, every physicist believes that observing takes more time than existing. But how much more? These existence intervals are the existence moments. In the existing reality, these are like points, let's say. They are moments of existence, but they are intervals in reality. Existence intervals. So, when the physicists think that everything is momentary, that is nice. It goes like this, but it's discrete. So, you have my body does not exist continuously. I am here, you think I'm here, but every part exists in different. It's a kind of puzzle, fuzzy puzzle which evolves and which fluctuates. And when you observe an average. An average of many manifestations. Because your observance is much longer. I would say there are billions of states of the universe in an observation. I will claim that, but that's empty, of course. Nobody can count it. But there are many, very many. Moments, existence moments are supposed to be very small. Observance moments, they depend on the speed of your brain, the speed of your tools, the connection, the interaction, the manifestations, and so on. So an observance interval for even just one observation is maybe billions of existence intervals. So what is the consequence of this? Let's say an electron, and I have an observed electron and an existing electron. And in the observed electron, this is so long, the observation, and here are many, and here's a break and a mutation, and another break, and another mutation. So this is the observance. Exist. So what are you observing? You think you're observing this manifestation. The first one you observe, begin to observe. You begin to observe manifestation. Initial. You know the thing exists, you begin to observe it, and you begin inside something. You could be an accident if it's on the end. But you probably begin to observe, and the observation interval is much longer. So, as I said, these things are different existing things. It's the same object as in the sequence, but they are different manifestations. It's not the same thing. It may be even different, small differences. Worse even, if after some time there is a mutation, then this is an electron E prime. There may be small differences. They say that electrons cannot be distinguished, but I doubt this very much, because the electron can be distinguished by some interior. We don't know the interior of the electron very well. Certainly not if you begin to say that it's a cloud of things or something. So there is a structure of the electron, let's say, a process structure. And the process structure can be different for E prime than for E. It is different, it's at another moment. So it can also have then different characteristics. Now, they will not observe that, because you see, observing, what do they observe? They observe OE. This has some characteristic. And they think that's an electron, the characteristic. But the electron is then, this observed electron is then an average of manifestations and mutations. There are at least two, because you cannot observe the first. The first is the beginning, and the observation takes longer. And there are probably a billion. Yeah. So, conclusion which I finish this by is that what exists, for example E, cannot be observed. The OE is what I call a super object. What is observed does not exist. So, it's a very crude, if you talk from moments and existence modes, it's a rather crude approximation to think that OE is E. And I will stop for today there. Well, that is the crux of the matter. En dan kun je natuurlijk